right? Do you, okay, it says, no, yeah, okay. Right. I think probably I won't even get that far. that is an absolutely enormous board. I've never seen such a large board. Okay, yes, so the title of my mini course is L2 Geometry of Modular Spaces of Vortices and Lumps. And we're going to start off with lumps. Have one lecture on lumps. And the advantage of doing that is that everything is extremely explicit. We can write down explicit solutions. We can compute the metric in a sense completely explicitly. And so everything's very sort of very explicit and conceptually very clear. And that's a sort of warm-up exercise to understand the L2 geometry of the modular space of vortices, where things are maybe a little bit more subtle. Okay, and I should also say, of the 4 lectures, all of the moduli space in 3 out of the 4 lectures are going to be non-compact. Okay, so non-compactness is going to be a very important theme which keeps recurring throughout these talks. Okay, but let's get started. So we're going to start off rather simple with the O3 sigma model just on 2 + 1 dimensional Minkowski space. Okay, so we have one field phi, which is just a mapping from R3 but with the Minkowski metric to the 2 sphere, which we think of as just being the usual round unit sphere sitting inside R3. So on this, I'm going to give this the usual Lorentzian metric dt squared minus dx squared minus dy squared. And the dynamics of that, so this is just an S2 valued function on 2 + 1 dimensional spacetime. The dynamics of this are going to be controlled by the Lagrangian density half d mu phi dot d mu phi. Okay, so the simplest natural Lorentz invariant Lagrangian density we could write down. Okay, so what do I mean when I say that the dynamics are controlled by that? Well, I just mean that we insist that phi is a formal critical point of the integral of this over spacetime. So phi is at least formally a critical point of the action, which is just the integral over spacetime of the Lagrangian density. Okay, so if we demand that, if we say our field has to be formally a critical point of this, so this has to be stationary with respect to variations of the field, we get the field equation associated with this action, which is rather simple. It's just a wave equation, but modified so that it makes sense, modified so that it keeps the field on the 2 sphere. So to take account of the constraint that the field is on the 2 sphere, it turns out that the Lagrange equation is that. Okay, where this operator here is just the wave operator, the Lorentzian version of the Laplacian. Okay, so we have this nonlinear wave equation. It's nonlinear in quite a profound way because the target space itself isn't linear, right? It's a manifold. Okay, well, it turns out that, as usual, because we have time translation invariance, solutions of that field theory conserve energy. So there's a conserved quantity called energy, which is just the integral over space, not space-time. So we just take a slice of constant time, and then we integrate half the square of the partial derivative with respect to time, plus the same with respect to the 2 Cartesian spatial coordinates. Okay, so it turns out that is a conserved quantity, provided phi satisfies the field equation. Okay, so in particular, if we think about the kind of fields that we're going to be interested in, well, we would like the total energy to be finite. Okay, so we like E to be less than infinity, and that motivates a certain choice of boundary conditions. So in particular, if you want this to be finite, so just think about it at a particular time, we want the integral over the plane over half phi x squared plus half phi y squared to be finite, then we should demand that these quantities here tend to 0 as you go off to infinity in the plane, right? So that motivates the boundary condition that as we go off to infinity, phi should go to a constant. And it doesn't matter which constant, there's a global SO3 symmetry here. So we might as well choose it to be the North Pole. Okay, so when we do that, now our field isn't just at a fixed time, isn't just a map from the plane to the two-sphere, it's a map from the plane where all the points at infinity get mapped to the same point on the two-sphere. So it's a map at fixed time. It's a map where we're taking the whole boundary as infinity and we're mapping it to the North Pole, which means that the field, you can think of it as having a continuous extension to the space we get by adding a point at infinity to R2. So it defines a map. Okay, where this marked point here, the point representing all the points at infinity, all gets mapped to the North Pole. Okay, so topologically, this is just another two-sphere. So this boundary condition gives us a well-defined notion of the topological degree of our field. Okay, so by taking this continuous extension to the one-point compactification, we get a continuous map from S2 to S2, and such things are classified up to homotopy by their degree, by the number of times that the map wraps this two-sphere around this two-sphere, counted with orientation. So we have a degree, topological invariant. The degree of phi, which is just we can write down a formula for it, it's just an integer. It's 1 over 4 pi times the integral times the area of the image of the map, if you like. So times the integral over the plane of this quantity here. Okay. So this you can think of as being the pullback of the area form on the two-sphere. So this is just the integral of the pullback of the area form. And then we're dividing by the area of the target space to compute the number of times that the field wraps this plane around the two-sphere. Okay. All right, so this is going to be a sort of recurring theme that we have a topological charge, an inter-value topological charge, which in a sense is going to tell us how many of our solitons we have in our field configuration. Okay, so next thing we want to think about is how the energy of a field depends on its degree. Okay, so is there some relationship between the degree and the energy? And there is, due to something called the Polyakov band. So this was first written down, well, it was written down in 1974 by Polyakov, but actually it's a rather simple special case of something much more general, which was already discovered by Lishnerovitz in 1970. Okay, so I'm going to present the argument as Polyakov wrote it down, but actually it generalizes hugely and was already known in its more general form several years before. So the idea is the following. If we have a field, so for the time being, we're ignoring time. So just imagine time's fixed and we're just thinking about a field mapping the spatial plane R2 to S2. What can we say about its energy? Well, what we can certainly say is that this quantity here, well, that's the vector product on R3, that certainly is not negative. And therefore, when I integrate it over the plane, I get something which is not negative. Okay, but on the other hand, if I imagine expanding out that square, what do I get? Well, I get integral of phi x squared plus integral of phi cross phi y squared, but phi y, since this is tangent to the two-sphere, it's orthogonal to phi. So taking the vector product with phi just produces a vector which is the same length as phi y, but at 90 degrees to phi y. Okay, so the norm squared of phi cross phi y squared is the same as the norm squared of phi y squared. So those two terms just give me phi x squared plus phi y squared. But then, of course, there's a cross term, which is phi x dot phi cross phi y, which if I use the permutation symmetry of this vector triple product is the same as minus phi dot phi x cross phi y. Okay, so I note that this is just the energy of a static configuration. So this is the energy of my field, my static field phi, and this is precisely minus 4 pi times the degree of the field. So I deduce that the energy of a static configuration of degree n is at least 4 pi n with equality if and only if phi x is equal to minus phi cross phi y. Okay. So note that this, so if I can find a solution to this equation, then any field satisfying that equation it minimizes energy within its topological class, therefore it's definitely a critical point of energy. And if it's static, that means it's a critical point of the action, which means it's a static solution. Okay, so any solution of this equation does solve the static field equation. But note that this is a first order equation, whereas the static field equation is second order. Okay, so this is rather nice. We've reduced the problem of finding static solutions to a first order problem. Again, that's a theme which you will see over and over again. Another nice thing about it is that actually this is really just the condition that the field phi is holomorphic. That's not immediately obvious. Let's just think about it. So one way to think of this, well, we can take the vector product of this with respect to phi. Okay, and on the left-hand side, I've got minus phi cross phi y. But if you think about what's taking the vector product, so here's the two-sphere. We've got phi. This is the tangent space of the two-sphere phi. So phi y, whatever it is just something which is tangent to the two-sphere. If I take the vector product of phi y with, of phi with phi y, I get something which has the same length as phi y, but I've rotated it through 90 degrees anti-clockwise. Okay, if I do that twice, I just get the same thing back again, right? I get minus phi y, so this is equal to phi y. Okay, so this equation actually implies this equation, and actually this equation implies this equation. Okay. All right, so why am I telling you that? Well, because there's a way of interpreting this pair of equations, which is rather natural and rather nice. Namely, I can think of these two things, my domain, the plane, and the two spheres being one-dimensional complex manifolds. And then they have almost complex structures. So on each tangent space, there's the action of multiplying a tangent vector by I, or in more geometric language, rotating it through 90 degrees anti-clockwise. Okay, and that's precisely what these two maps are doing. So on the plane, which is the domain of our map, we have the almost complex structure. What does that do? Well, it maps d by dx to d by dy, and d by dy to minus d by dx. And on the two-sphere, again, we have an almost complex structure. What does it do? Well, to a tangent vector, that's just a vector orthogonal to phi. It maps it to phi cross v. Okay, and then both these equations are just saying, if you think about it, so this is saying that, if I move the minus sign here, this is saying that the image under the differential of the image of d by dy with respect to the almost complex structure on C is precisely the same as the image of the tangent vector d by dy under the differential phi, followed by the almost complex structure on the two-sphere. Okay, so in other words, and swapping d by dy for d by dx, you get an interpretation of that equation there. So in other words, what we have is that E of phi, so remember where we were here, this is the condition for phi to attain this topological lower bound on energy. E of phi is bigger than or equal to 4 pi, and furthermore, we have equality if and only if the differential of the map commutes with the almost complex structures. In other words, phi is holomorphic. Okay, so this again is something which you're going to see over and over again. Topological energy bound. The fields which saturate the topological bound, they satisfy the field equations, which are second order, but they satisfy something stronger, a first order system of equations, which have something to do with holomorphicity. So here it's very, very simple and very plain. The Bogomolny equation, if you like, is the condition that phi is holomorphic. Okay, so we can exploit that to actually write down all the static solutions of this model. Okay, just by choosing a complex coordinate. So on our physical plane, we can just choose a complex coordinate z equals x plus iy. And on our target space, we can equip that with a complex coordinate by stereographic projection. So if we do a stereographic projection from the South Pole, the equatorial plane, so that takes points there and maps them. So to each point on the two-sphere, apart from the point that you're projecting from, you just draw the straight line from the projection point through that point and see where it hits the equatorial plane. Let's call that coordinate W. So I think the formula for it is phi1 plus I phi2 over 1 plus phi3. Okay, so we can express a function which, if it's going to satisfy this condition, if it's going to saturate this bound, has to be holomorphic. If we use complex coordinates on the domain and the target, then this condition here really does reduce to the Cauchy-Riemann equation. Okay, so this in this language is just the condition that W is holomorphic in the usual sense. Okay, but remember, this thing is allowed to take the value infinity. In fact, it will have to take the value infinity because every time it hits the South Pole. So as you go off to infinity in space, the field has to go to the North Pole, which is W equals 0. But there are going to be points in the interior of the plane which get mapped to the South Pole, which is W equals infinity. Okay, so this is going to be a holomorphic function. Sorry, it's going to be a holomorphic map to the two-sphere, but it's not a globally defined holomorphic function because it has to be able to go through the South Pole where it's going to have poles. Okay, so actually this is a meromorphic function. Okay, so we can write down the most general meromorphic function of degree n. It's just going to be a quotient of two polynomials, at least one of which has degree n, and they don't have any common roots. So maybe I should check that I'm still on track. Yeah, so the general static solution looks like this. Okay, where these are just complex constants. And they're not completely independent of one another because the numerator and the denominator is not allowed to have any common roots. Okay, otherwise the degree would drop down. Okay, so obviously, if you multiply all these coefficients by the same non-zero complex number, you get the same solution as well. Okay? All right, but remember there's a boundary condition. The boundary condition was that as you go off to infinity in space, you should approach the North Pole, which is W equals 0, because we're projecting from the South Pole. So W of infinity equals 0, from which we deduce that actually the numerator must have strictly lower degree than the denominator. Okay, so actually this term here is missing. Okay, and this term here has to be non-zero, so I can divide everything by the coefficient of this. And okay, and my general solution now looks like that, where A0 up to AN minus 1 and B0 up to BN minus 1, they're all just complex constants. Okay, so if I think about what the moduli space, and calling it a moduli space is a bit overkill, really. We're not really quotienting out by anything here. But anyway, in this, we still call it a moduli space. It's just the parameter space of static solutions of our problem, basically. Call it MN. What is it? Well, it's the space of degree n rational maps satisfying a basing condition that the point at infinity gets mapped to 0. Okay, so this is just an open subset, if you like, of C2n, right? So you've got A1 up to AN minus 1. Sorry, A naught up to AN minus 1, B naught up to BN minus 1. So collectively, that's 2n complex constants. You have to remove the subset on which these two polynomials have common roots, which is a complex codimension 1 subset. And what you're left with is an open subset of C2n. Okay? Okay. All right, so that's all static. But we started off defining this model on 2 plus 1 dimensional spacetime and talking about dynamics, right? The field equation is a nonlinear wave equation. So the interesting question is, what do time-dependent solutions look like? So-called wave maps. So solutions to this are called wave maps. And the answer is that's very hard. This is not an integrable PDE, although you can write down the static solutions very explicitly. There are no methods for actually writing down, in general, what time-dependent solutions look like. So we need to somehow find an alternative way of understanding the dynamics. So let's think about the following kind of Cauchy problem. For this PDE. For this hyperbolic second order PDE. So we're going to assume that at time 0, field is an element of the moduli space. Okay, so it's a degree n rational map. And we're going to assume that its time derivative is tangent to the space of holomorphic maps. Okay, so one way of developing such a field, in fact, the only way of developing such a field, is to pick one of these rational maps. Okay, so pick values for these coefficients. Now imagine allowing those coefficients to vary with respect to time, take a derivative with respect to time, set t equal to 0. Okay, and you get one of these tangent vectors that I was talking about over here. Okay, but we're going to assume that this vector, whatever it is small. Okay, and now let's think about the energy. Remember, total energy is conserved. Okay, so that's whatever it is, it's always the energy at time 0, which is 1/2 the kinetic energy plus the integral of phi x 0 squared plus phi y 0 squared. But remember, this was chosen to be holomorphic. It was specifically chosen to be one of these maps where we get equality in this bound. So the static energy is just 4 pi n. Okay, so our conserved energy looks like that. It's this quantity here, which is the absolute minimum that any field in the topological class of degree n could possibly have, plus this, which we're assuming is small. Okay, and that's the energy for all subsequent time. Okay, so given that this is small, your energy is never very far above the topological minimum, it's natural to assume that the field can't get very far from the set of fields which attain this minimum, right? So conjecture, phi of t never strays far from the moduli space of static lumps, the space of holomorphic maps on which the energy, the static energy, has its minimum. Okay, so the picture we have in our heads is something like the following. If you imagine the space of all fields, so smooth degree n maps, from C to S2, of course, that's an infinite dimensional space, and putting a topology on it is hard work and so on. This is all very informal. Then inside it, we've got the space of holomorphic maps, which is a 4n dimensional manifold on which the energy, the static energy, which is just half the integral of phi x squared plus phi y squared, attains its minimum. Okay, so E is 4 pi m. And if we deviate from that manifold in any way, then the energy goes up, the static energy goes up. So what we have is a 4n dimensional manifold sitting inside the space of all fields on which the energy attains its minimum value. And we're imagining the situation where we start off on the bottom of that valley bottom, in the bottom of that valley, and we give our field a very small push tangent to the valley bottom. And then we ask ourselves, what happens, according to the wave map flow, what happens to the field subsequently? Okay, well, our conjecture is it can't get very far from the manifold, from this manifold Mn, which leads further to the conjecture that it should be a good approximation to constrain the field so that it always lies on Mn. So approximation. So assume phi of t is actually on the manifold for all t. Now, this is certainly going to be an approximation, right? It won't literally stay on the manifold. Okay, so we're going to approximate the solution of the actual field equation, the wave map equation, by something else where our field is only allowed to vary through static solutions. So this is often called an adiabatic approximation. Okay, so how do we get dynamics in this approximation? Well, we take a field of this form and then we substitute it into the action which defined the original field. Okay, so that's the integral over time of the integral over space of 1/2 phi t squared minus 1/2 phi x squared minus 1/2 phi y squared. Okay, so we take the same action we had to start off with, but we just restrict it to fields which at each fixed time lie on the manifold of static solutions. If we do that, this is very simple, right? The integral over space of this quantity here is exactly 4 pi m. I mean, that's how these fields were chosen. Okay, so this is equal to the integral with respect to time of this quantity here minus 4 pi m. Okay, so this is just a constant, which is irrelevant when we do the variational calculus, so we can just throw it away. Okay, so our new variational problem is we're going to take our field phi, which, remember, we're assuming it's of this form. So each fixed time, it is a degree n rational map. Okay, so that's how our field depends on time and space, and we take that and we just plug it into the action. Okay, and the only things we're allowed to vary now are these complex numbers, a0 up to bn minus 1. Okay, so if we do that, I mean, let's call these things collectively a0 up to an minus 1. Let's call them qi. Let's call this w of z qi of t. So these are the a's and b's. Okay. So if I imagine plugging that into here and doing the calculation, what do I get? So it's the integral over time of the integral over space of 1/2 phi t squared. Okay, but a half phi t squared, sorry, when I say phi, I don't mean that. This is, of course, W. So phi is the map which takes t, x, y, and maps it to W equals that, equals W of z, qi of t. Okay, so I want to take the time derivative of that and take its length squared with respect to the usual metric on the two-sphere. So what's that? Well, that's the same as 1 over, sorry, it's the same as 4, I should say, over 1 plus W squared all squared, dW by dt squared. Okay, so that's just using the usual expression for the round metric on the two-sphere written in stereographic coordinates. Okay. But the only time dependence I'm allowing is I'm allowing these parameters, these the complex parameters which I'm collectively calling Qi, to depend on T. And these things, these depend, if you think about the dependence of W on the parameters Q, that's obviously holomorphic, right? So this is the same as that, okay? So now I can take this lot here. What are they? They're just complex numbers which depend on the parameters Qi, and I can call them Qij. Okay, and then what I have here, sorry, let's take the half out. What I have here is precisely the Lagrangian or the action describing geodesic motion in the space parameterized by these parameters Qi with respect to the metric whose coefficients are Gij. Okay, so this is geodesic motion. In Mn, which is the space of base degree n rational maps, with respect to the following metric. Sorry, G equals Gij of Q, dqi, dqj bar. Okay, this metric is called the L2 metric. So in the title of my mini course, I talk about L2 metrics of moduli spaces of blah, blah, blah. What do I mean by the L2 metric? Well, in this case, I mean precisely this metric here, metric which has this explicit expression. It's the metric you get by restricting the kinetic energy of the original field theory to the moduli space of static energy minimizers. So what properties does it have? Okay, so you can imagine, substituting in this explicit expression here, and you end up with an actual integral formula for the metric coefficients, right? So in this situation, we actually can write it down very, very explicitly. One thing we could note about it is the following. Well, first of all, if you think of these coefficients here as being the components of a 2n by 2n complex matrix, it's obviously Hermitian by definition. Okay. And that means that the corresponding metric isn't just a Riemannian metric, it's a Hermitian metric. So the metric is Hermitian. Which means that the almost complex structure associated with the complex structure defined by the fact that these coordinates here are complex, right? That's an isometry. So for all x and y, tangent. In that situation, there's a naturally associated two form associated with the metric called the Kähler form. Okay, and it turns out that it's not hard to show, at least formally, that this Kähler form is closed in this example. Why does that follow? Well, a nice way of writing down these coefficients is the following. You can always think of it as being the integral over the plane of d by dqi, d by dqj bar of the logarithm of 1 plus norm of w squared. Okay, so if you just compute this and compare it with this expression here, you'll see you get the same thing. Well, modulo possible factors of 4, which I always forget about. And from that, it follows, at least formally, that if I take the qj partial derivative, sorry, the qk partial derivative of gij, that's exactly the same as this partial derivative. So the partial derivative where I switch these two indices here, it's symmetric under that. And also, I do the same thing, but differentiating with respect to qk bar. Again, they're the same. So these identities follow immediately from this expression here. Okay? Formally, at least. And from that, it follows immediately, just if you just compute the exterior derivative of w and use these identities, you get that this is a closed two form. Okay, so actually, this metric, the L2 metric on the space of rational maps, it isn't just a Riemannian manifold. It isn't just a Riemannian metric. In fact, it's a Kähler metric. Okay, so the metric structure and the complex structure defined by these complex parameters, they play very nicely together. They're very compatible. Okay, so this is all looking really nice and beautiful. But now I have to tell you the dirty secret, which is that actually all of this didn't really make sense. Okay, so there's a problem. This metric is not really well defined. Okay, so I guess I should have said before I started, let's think about the simplest possible moduli space. So M1, what's that? That's the space of degree 1 based rational maps. So that's a degree 0 polynomial divided by a degree 1 polynomial. So that's something of the form lambda over z minus z naught. Okay, so that's lambda is a non-zero complex number, and z naught is just any complex number you like, right? So the moduli space in that case is this nice four manifold punctured complex plane cross complex plane. This parameter here, well, this parameter here is very easy to think about. It represents the position of the lump of energy. So if you compute the energy density of this thing, it's spatially localized around z naught. So this is energy density. Okay, and the parameter lambda is modulus is telling you about how wide the lump is. It's telling you about the width. But it's also telling you about the internal orientation of the lump. So if you change the complex phase here, you just rotate the lump about its axis. So width stroke orientation, they're controlled by this parameter here, and this is just position. Okay, so the one lump moduli space is nice and simple. What about the metric on the one lump moduli space? Well, unfortunately, the metric on the one lump moduli space is ill-defined. Okay, so in particular, if we think about the metric, we think about the length of the parameters curves corresponding to lambda. With respect to this metric, what do we get? So that's just the integral. It's 4 integral over the plane. dw by d lambda squared over 1 plus w squared all squared. So everything is independent of Z0. That, you know, changing Z0 just translates everything. So we might as well set Z0 to 0. And what we end up with is the integral over the plane of 4. dw by d lambda is just 1 over z. Okay? So it's just that. It's just literally this function of lambda, modulus of lambda. Okay, but of course, we're integrating over a plane, so, and everything's rotationally symmetric, so we can think of that as being 2 pi times the integral. The radial integral, now I get a factor of r from the integration measure, times 4 over r squared over 1 plus lambda squared r squared all squared. And you will see that this, so if we multiply top and bottom by r to the 4th, we get that. Okay, so the integrand only decays like 1 over r. And you try and integrate it over the whole plane, over the whole positive real line, it diverges. So this is log divergent. Okay, so yeah, formally, the L2 metric has these nice properties. It's formally Kähler, formally Hermitian, all that. But unfortunately, it's not actually a well-defined metric. Now, you can, if you like, try and rescue things by saying, well, okay, what's the physical message of this calculation? What it's saying is, yes, this is a free parameter in my static solution, but changing it costs infinite kinetic energy. So changing this parameter here is impeded by infinite inertia. So maybe the message is we just take it to be constant because we have only a small amount of energy, so there's no energy to change it. Okay, so the sort of naive thing you could do is say, well, lambda is fixed. Okay, and then we just so we move not along we move along the leaves of a foliation of the moduli space where we fix the parameters which are not allowed to move because they have infinite inertia. Okay, well, what would that tell you? In that situation, the reduced moduli space for fixed lambda would just be the complex plane, right? Parameterized by Z0. Okay, and the metric would be very simple. You can compute it. It's just the Euclidean metric times the static energy of the king of the lump. Okay, so what this approximation would say is, well, one lump dynamics in this model is totally trivial. They just travel in straight lines and don't change shape. Okay, that's all they can do. Well, of course, there are solutions where lumps just travel in straight lines and don't change shape at constant speed by Lorentz invariance, but they're very special, and in general, the dynamics is much more complicated than that. So if you solve the PDE, there are much more interesting things than that can happen. In particular, real wave maps can collapse and form singularities in finite time. So this is, I mean, that's a rigorous theorem. It took absolutely ages to prove that this is true. It wasn't until 2008 that it's finally proved that wave maps can collapse and form singularities in finite time. But this is a well-known phenomenon now. So trying to rescue things by doing this very simple, sort of physically motivated assumption that the moduli with infinite inertia are fixed by their infinite inertia, that's really hopeless. It misses out all the interesting stuff. Okay, so what can one do? Is there still something non-trivial that we can rescue from this whole thing? The answer is yes. What we can do is we can change the problem we're working on. So instead of thinking about wave maps on the plane, why not take physical space to be a compact Riemann surface? Okay. So we can remove the singularities by taking physical space, not space-time, but physical space, to be sigma, a compact Riemann surface. Okay? And then it turns out that the Polyakov band goes through exactly unchanged. So it's still true that E is bigger than or equal to 4 pi n with equality if and only if phi, but now it's a map from a compact Riemann surface. S2 is holomorphic. Okay, and we can still define the L2 metric in exactly the same way that I did before, but now rather than taking a space of rational maps, they're not necessarily going to be rational maps anymore. They're just holomorphic maps from our compact Riemann surface to S2. Okay, so now the L2 metric is still, it's definitely well defined because the integrals defining it are now integrals over a compact space, and nothing, this problem just can't arise. So now the L2 metric G is well defined. It really is Kähler now. It's not just formally Kähler. The argument that I went through there, you can make it into a theorem. And you still have this hope that because this picture that I'm in the process of rubbing off, because the space of holomorphic maps is this valley bottom, you still have this hope that if you start off at a holomorphic map tangent to the space of holomorphic maps with low kinetic energy, the subsequent wave map flow will stay close to the space of holomorphic maps. Okay, so we can do this for any compact Riemann surface we like. Which one should we choose? Well, whenever you want to choose a compact Riemann surface, there's only one that's worth considering, and that is the two-sphere. So the nicest case, so I'm trying to get a rise from Nuno there, but anyway, it doesn't work. The nicest case is where I just take my compact Riemann surface to the two-sphere. Why? Well, because then I can just use, on the two-sphere, I can also use a stereographic coordinate. So my stereographic coordinate here, let's call it Z. Stereographic coordinate here, call it W. So the formula for the static lumps is exactly the same as it was before. They're still just rational maps. Okay, except now I can't assume, there's no basing condition anymore, there's no boundary in infinity. So I can't assume that the numerator has a strictly lower degree than the denominator. And therefore I should take these coefficients here and think of them not as just being complex numbers, but defining a projective equivalence class of complex numbers. So the point is, if I take, the rational map corresponding to these parameters is exactly the same as the rational map corresponding to the same parameters, but all multiplied by a non-zero complex number. So I should really identify this with not the point A0 up to Bn in C2n plus 2, but its projective equivalence class. Okay, because multiplying them all by the same complex numbers doesn't change anything, right? So I think of this as being an open submanifold of CP2n plus 1. Okay, and it has a metric on it. And it really is Kähler, and you can prove various things about it. So quite a lot is known about these metrics in general, but I only have 6 minutes left. So I don't really have time to tell you very much. Let me just tell you a little bit about RAP1. So e.g. n equals 1. Oh, not 55 minutes. Okay, so I don't have any time left. No, that's fine. I can. Well, let me skip to the punchline then, which was, if you do this, everything's well defined, and so the L2 metric is well defined. There's a well defined flow. One thing I should tell you is that this is always geodesically incomplete. So MNG is geodesically incomplete. So there are geodesics of finite length which hit the boundary at infinity, which corresponds to these things acquiring a common root and the degree dropping. Okay, but that's good because that corresponds to a singularity forming in finite time and the thing collapsing. And that's exactly the kind of behavior which PD analysts have proved wave map flow really does have. Okay, so the fact that this is incomplete is not a flaw of the approximation. It's actually a feature. It is good that it's incomplete. Okay, so let me just finish by saying the theorem then. So this is all an approximation, right? We're saying if we start off on this valley bottom, moving slowly with an initial velocity vector which is tangent to the valley bottom and small, then the wave map flow, which let me remind you is a solution of this PDE, remains close to the geodesic with the same initial data. Okay. Okay. Well, it turns out that's not just an approximation. It's not just hand waving. There's a theorem which says that's literally true. So let me just state this theorem and then I'll stop. So this is by me in 2012. So if we consider the one parameter family of Cauchy problems, where your initial field is in the space of holomorphic maps and your initial velocity is epsilon. So this is the one parameter family I'm talking about. This is the one parameter where V is tangent to the space of holomorphic maps. Okay, so consider that one parameter family of Cauchy problems where the parameter is just scaling the initial velocity. Okay, then the theorem is that there exists epsilon star, tau star bigger than 0, such that the Cauchy problem, there exists a unique solution to this on an interval which gets bigger as epsilon gets smaller. Okay, and it's smooth and all that. That's not the interesting part. I mean, that's kind of obvious from standard PE theory. The interesting thing is if you take the time rescaled solution. So further, okay, so if we define the time rescaled solution, let's call it phi epsilon. So this is just the thing which maps a rescaled time tau and a point P to phi of tau over epsilon times P. Okay. So this is now one parameter family of maps from this fixed manifold to S2. This converges in C1. So in the set of continuously differentiable maps from here to here, given its usual norm, given the uniform C1 norm, as epsilon goes to 0, that converges to the geodesic. In Mn with respect to the L2 metric with initial data phi 0 and initial velocity V. Okay, so in this particular situation, this approximation, which had this physical intuition behind it about valley bottoms and so on, it can be turned into a very precise, rigorous theorem. Okay, it really is true that if you study the wave map problem where you start off with a holomorphic map with an initial velocity vector tangent to the space of holomorphic maps and small, in the limit that you take the velocity to 0, the thing really does converge in this uniform sense to the corresponding geodesic. Okay, and that's something you can prove. And I've already gone over time, which is not a great start. I mean, this is, I think, precisely when you throw away the gauge group, right? These are basically ungauged versions of what you're talking about. I mean, I don't really know how to answer the question. What I can say is that there is a parallel story for the things that you're talking about, I believe, where again, you have a modular space of static solutions, which are these things you're talking about. And again, there's a natural L2 metric. And again, there's a Lorentzian version of the theory where there's a dynamics and it's a conjecture that the geodesic flow in the modular space of static solutions is a good approximation to the Lorentzian dynamics. And in fact, that's what we're going to start talking about tomorrow. Other than that, I'm not quite sure. Yeah. There are parallels. I'm not sure. Well, yeah. Okay. So, yes, I guess one very direct thing that you can do is you can think of the space of holomorphic maps. You can consider a gauged version of the model where your field is living in C2 and it's a U1 gauge field. But you can consider a limit where you take the electric charge off to infinity, so the sort of gauge orbits collapse. And then formally, the moduli space of that gauge system converges to the space of rational maps. Okay, and again, there's an L2 metric in this moduli space of gauged things. There, the moduli space is compact because you don't have this problem that you don't have to exclude points where the things which are going to infinity and the things which are going to zero are coincident. And therefore, you can just use cohomology to compute the volume of the modular space because it's compact. So if you know the cohomology class of the Kähler form, then that's good enough. So you can compute the volume and then take this limit, and conjecturally, you get the volume of these things. Okay, so there's, yes, it's true that you can get insight. I think the insight, as far as I know, the insight goes in that direction. So the insight, you get insight from the gauge things into the ungauged things. Or, yeah, I'm not sure knowing about this geometry tells you much directly about going the other way, because you've had to take a limit to get from one to the other. So I'm not quite sure you're asking. So I mean, this thing is literally just satisfying the geodesic equation in M and G. So that's just an ODE basically, right? System of ODEs. Whereas this is a PDE. I mean, so the way you relate the two is you say, well, let me take a curve in MN, and then associated to that curve, let me construct a field mapping time across sigma to S2. Okay, so you just, so let's assume this is a wave map. Okay, so it satisfies this PDE. Okay, and let psi be some curve in this moduli space. And let me define this thing, the error section, so that the difference between those two things to be this thing y. Okay, you then substitute that into that PDE there, and you get a PDE for y, okay, which has a certain structure. You then demand that y is L2 orthogonal to the tangent space, the moduli space. And it turns out that this condition here is where the geodesic, this is the condition which actually forces this to be close to a geodesic. Okay, so yeah, that's how you get the flow for this thing here. And it's not obvious that it's going to be close to geodesic. You actually have to do some calculations to see how the two things are related. But that's the idea of the proof. You express your wave map in this form, and then you basically just do estimates to bound the growth of this error section here. That's how the proof works. Yep. Yes. that's it. Yeah, I mean, so yeah, I mean, you can prove stronger things than this. So I started off with a Cauchy problem where you start off on the modular space tangent to the modular space. You can say, well, let me start close to the modular space with a vector which is close to the. In other words, you can add an order epsilon corrections to the position and initial velocity and still prove something of this form. Okay, but this is a sort of nice clean version of something you can prove. Yeah, that's it. So and note that all it's saying is that the solution remains close to the geodesic for times of order 1 over epsilon, where your initial velocity is of order epsilon. Okay, so this doesn't tell you that it remains close forever. Okay, so if you remember, the modular space here is incomplete. So there are geodesics which hit the boundary at infinity in finite time. It doesn't follow that this is a good approximation all the way to the boundary. Okay, so this tau star might be less than the time that it takes to hit the boundary. If you have a geodesic which doesn't hit the boundary, it doesn't follow that the wave-map flow remains close to the geodesic for all time. So yeah, it's something, but it isn't fantastic. Yeah. I mean, so if you're interested in dynamics around the actual time of scattering, then a theorem like this tells you. So, for example, we're going to talk about vortices next time, which are just they're just specified by their position in the plane, right? And if you fire them towards one another, they famously form a ring structure, and then they split apart in 90 degrees. So the fact that this happens, yes, that's a version of this theorem, but for vortices, which was actually proved before this theorem, does tell you that for a time containing the point of scattering, the dynamics is well approximated by the geodesic. But it still doesn't tell you that, doesn't tell you directly that the subsequent evolution off to infinity is correct. Now, probably for this problem, if you tried hard, you could probably prove that, because as they go off to infinity, of course, all the interactions are exponentially suppressed. So I would imagine you can directly show that the dynamics, when they're very well separated, is well approximated by them just going on straight lines. But that's very special to this. So yeah, it says that for these kind of theorems always are of the form that the real solution stays close to the geodesic with controlled errors for times of order 1 over epsilon. And that's, as far as I know, that's the best anyone's ever done. And for the wave map flow, there's a good reason for that. You couldn't get better than that because of the incompleteness and because of the actual singularity formation. But for things like this, where the motion is complete, you could hope to do better, but no one ever has. Okay, thanks very much.